analysis work that needs to occur when you get a report of potential issues is eradicated, because you're eliminating the false positives, and the idea is that you're generating test artifacts that are going to let you go back and confirm if the issue has been removed after you made updates to the software. And the really nice thing is this can be done both in the host or in the target environment, because sometimes there are issues that may manifest themselves in one particular area but not in another area. So some examples of problems that we've been able to find. So through the analysis of open source projects, a number of API usage related issues have been identified, and we'll talk about this a little bit more later in the presentation. Just in the theme of the presentation that occurred before, we did some work with an automotive tier 1 that was building a telematics system, and by running this analysis we were able to find about 400 to 500 issues in the application which could have been potential security vulnerabilities, and this was all done automatically, so there wasn't really any human analysis required there. It was basically, these are potential issues and you need to fix them, otherwise someone could take advantage of the system. And this was code that had been been through static analysis. And so, but typically we're sort of looking at the kind of issues like null pointer dereferences, classic buffer overflows, or improper resource shutdown and release. So the typical kind of issues that could be used to do denial of service or potentially be used to take control of a system. And there are associated CWE codes with those kind of errors. So security weaknesses of interest. So the approach is focused on automatically generating tests for a number of classifications of vulnerabilities according to this MITRE standard. And so typically what we're focusing on is the area of indication of code or poor code quality. And this is basically the CW398. And inside there, some of the issues that we're really trying to focus on are hard errors. So things like the null pointers, the buffer underflow, overflow, stack corruption, divide by zeros. Mismatch calls, so a mismatch of calls between malloc and free, where you might have a leak situation, or you might be incorrectly calling free more times than you call malloc. fopen, fclose, and then pthread, so like mutex type activities as well. Bad arguments to memcopy, which again can be used to overwrite memory and then be able to let you again take control of the system. And then unchecked returns from malloc as well. So how does it work? So the principle is very simple, and that's the beauty of this approach. We basically take an issue, we build a test vector to exercise that particular path. So if we take the example of a pointer related issue or a memory allocation issue, we take the test that allocates the pointer, we remove the allocation, we rerun it, and then we just validate if it crashes or not. And if it crashes, then you have a real issue there that you need to address. There isn't any ambiguity there. So this kind of testing is called fuzz testing, and it's very exciting. So we took an example here of an open source project called Lighty. And this was one of these issues that sort of came up in the static analysis conferences, comparing the different tools and how they were able to find it and how they were able to, basically let the user know clearly that there was an issue. And so you can see in this example here, there's an issue if we pass a null pointer into B, that basically it can be dereferenced without being checked, that it's a null. And so there were a few different tools that were used here. So CPP check, Facebook's tool Infer, basically said, there are no issues, this code is clean. Tools like Lint and Codehawk identified it as a potential issue, but didn't really say you must fix this. And just by looking at this example here, it's very clear that there is a programming issue. And so with a tool like VectorCast, it was able to automatically build a fuzz test case to exercise this particular path. It was able to set, the variable B to a null pointer and really confirm if there was an issue. And that was done all automatically. There was no humans involved in analyzing and trying to build that test case. It was all done through the analysis of the code. And so that's quite powerful. And it basically gives a clear indication to the user there's an issue here. So some of the benefits. So So this is kind of a white box unit testing. It's not black box dynamic application security testing, or DAST as it's referred to in the industry. Static analysis might not detect it, so there are, the false positives are very high in static analysis tools. Is it a real error? And a variety of the companies use different approaches for dealing with the challenge of static analysis tools. There might also be false negatives, so maybe they don't show that an issue exists because they struggle to exercise that path. So with dynamic execution, again, we're not trying to be completely exhaustive here, trying to run this thing to complete end, so trying to solve the halting problem. We can't catch every bug, but what we can do is basically focus on a core set of issues and determine if there really are any problems. So the nice thing is, if we do find something, it really is an issue. And you can fix the issue, regenerate the environment, re-execute the test, and then if the error goes away, the issue is fixed. And this also solves the other problem, that is, if a static analysis tool told you there was an issue, typically there might be a situation where you change the code, and by changing the code you just hide the issue. So it still exists, but it now exists in a path that the static analysis tool finds more difficult to be able to correctly identify. So, or hides under a false negative. So now that we have this information, we can start talking about actionable intelligence, so metrics towards driving better quality and higher reliability and higher security in applications. So we start talking about things like application security. So there are three main parts that we talk about. So there's identify for the process. So identify the portfolio. So identify the applications that you want to work on, and this might involve incorporating a number of business units, procurement, vendor management, thinking about the regulatory impact as well of these applications, data leakage risk, operational risk, and using that, identify the applications that are really important to be taken as part of this process. You need to assess the vulnerabilities. So you need to identify, how can people take advantage of this? Is this on an open network? Is it on a closed network? Is it going to be a trusted user that's going to make a malicious attempt? Or is it potentially any user that can get in there? And then you need to manage the risk. So you need to come up with a risk analysis of what happens if someone is actually able to take advantage of the situation. And what you might find is that some things that you consider that are non-issues or mitigated against as part of your software architecture. But one of the interesting things here that's very good, but typically we know in the software industry we talk a lot about reuse. So there might be assumptions that you make in application A that when you deploy it in application B, all of a sudden some of those assumptions are missing, and now you've opened up a potential issue in the application. So a classic example is we allocate some memory, we check that memory, and then further down the chain we basically don't check it again. And then application B comes along and takes some of that software much lower in the chain and misses the check for the potential memory allocation issue. And so now we have a potential issue in the application. So easy metrics. So again here, the Chess Morningstar came up with a nice way of basically, tracking or quantifying the issues with software. And basically giving like a star ranking system. So there's a 5-star ranking system. So the first star is basically the absence of remote and or set UID vulnerabilities. The 2 stars is basically the absence of obvious reliability issues. Then 3 stars is you follow best practices. 4 is documented secure development processes, and 5 stars is passed independent security review. So for us, the area that's of interest is the 2 stars. So the absence of obvious reliability issues. But this kind of thing is very binary. Either you have issues or you don't have issues. So you have the challenge here that if you have an application and it has 1 vulnerability, you're not able to get to 2 stars. And so we'll talk a little bit later on about how we can maybe start weighting all these issues and coming up with more complicated metrics. But as a very simple first step, the Chess Morningstar sort of, for software security kind of star system is a very good way to start that process. So, So there are some easy ones, and things like, defect density, so defects per software lines of code, lines free from obvious issues via code coverage, so confidence of defect freedom. So if you've exercised all of your software, you can have some level of confidence that, you've at least dealt with some of the more obvious issues. And then the ratio of security tests free of defects. So again, tests that you run that are free from any potential issues. So obviously higher ratio means your application is much more secure. And then there are more involved metrics. So starting to look at exploit depth. So is it at one level, or is it many levels deep in the stack that I can exploit a potential issue? So obviously the deeper we're able to go, so if we put a null pointer in up here and 5 levels lower we're able to exploit something, that's a very big issue. And so that's higher criticality that needs to be addressed. What's the criticality of the issue? So that we have this terms, the common weakness risk assessment framework, and then the common weakness scoring system. And so the idea of this is to start assigning weightings to the potential issues that you have, and to come up with a scoring system so that some issues have far greater risk than others. And so if you can assign a weighting to the criticality of the issues, this again gives you a better, more pragmatic view of the issues in your system, instead of a binary sort of chess morning star where it's yes it has issues or no it has no issues. And then also looking at the correlation between function complexity and the number of defects. So there's a lot of research in this area, and we'll talk about in a few slides down about how, if you have functions that have a complexity greater than 20, they're usually at a higher probability of containing issues and potentially security issues as well. Percentage breakdown of metrics by type or grouping, and then attack surface. So, are the defects via parameters, or are they returns by stub? So, for example, if I call malloc, if I call message receive, can I, if message receive provides something invalid, can that cause a potential issue in my application? And that's obviously a big issue. So, what we did was we actually did a case study of 3 open source projects. So, Lighty, Zadlib, which is used, in SSL and Apache, and then libxml too. And one of the areas that we were looking at is, looking at the complexity of functions and looking at the correlation between that and the potential sort of issues that exist in it. So basically what we did is we took these projects, we built fuzz test cases. So this is basically where we analyzed all the parts through the software, and we built test vectors to exercise all those parts, and then we started mutating them. So we started saying, well, what if we put an integer value is out of range? Or what if we pass it in with an integer value that's 0? Or if we pass it in with a pointer that's invalid? Or it's being used in an array dereference and we pass in a very high value. And so going through that exercise, we came up with the situation here where we were typically able to sort of, come up, so something like 709 issues for Lighty, 113 for Zadlib, and 2,926 for libxml. And so you can see here between all the applications, they typically have a very similar defect density. So that's kind of a nice correlation across all the projects. And here you can see, the average number of tests per defect as well. But what becomes more interesting is that when we start looking at libxml, you can see here that, they have roughly about 40% of the tests are hitting defects, but about 29% of those functions in libxml are the ones with all the issues, and a high percentage of those issues are in functions with a very high complexity. So again, this kind of feeds back into the research that Capus Jones has done, that if you're trying to address security, one of the most pragmatic things that you can do up front is to try and build functions that don't have very high complexities, because that's a high correlation to issues in the application. So some real world examples. So these are examples that we've done with applications, real customers. We've obviously hidden their names. But here this is a medical devices customer. And so this is a very interesting situation here, because a lot of the code here was extremely judicious in checking all of the parameters, making sure that there are no issues. But in this particular example here, they were basically receiving a pointer to a structure, but they were never checking if the structure was valid. And so there was a potential here that this could result in some sort of invalid memory dereference, which could then result in a failure in the system. So that was one example, and this again was done with very minimal human effort. This was all done with sort of machine intelligence and analysis of the code. Another one is a divide by zero issue here. So here in this example, you can see in the code, the user or the programmer in many areas is checking the values of certain parameters and making sure that, if the value is not invalid and it's not zero, but still at the end, they then progress to actually do a divide operation where the value could potentially be zero or even uninitialized in some of the parts. And so this was one that this is actually in something that's driving around today. It was an issue that was found. And so there's no guards against that. So the take home. So the big thing here is, there's no one-size-fits-all solution, so you need to use multiple tools. Dynamic execution is a very good way of very quickly and efficiently identifying issues in your application. So it gives you actionable intelligence, hard facts, not false positives. You always need to look at damage potential versus effort. And there are a number of metrics as well that you can use to help decide how you sort of deploy this within your project. So some future work that is very interesting for us is how metrics can be used to predict vulnerability. So given a certain application, if there are other applications in a similar class or certain signatures in a particular function, how that can be used to predict ahead of time that this particular flow of software typically results in errors in this area. So maybe this is the area that should be automatically exercised to confirm if the new application has the same kind of issue. Thank you. We'll do questions at the end, right?
Okay, thank you very much, Niro, and our next speaker.